Hello all. In this lecture, we will continue the discussion of relation between differential and integral equations. In the previous lecture, we have already seen that an initial value problem can be converted into a Volterra type integral equation. Similarly, in this lecture, we will show that a boundary value problem can be converted into a Fredholm integral equation, an integral equation of the Fredholm integral equation type. Okay, so let's consider a boundary value problem. Boundary value problem means a differential equation with boundary conditions given. That means the conditions prescribed on both the endpoints. Okay, so consider a simple boundary value problem d square y by dx square plus lambda y equal to 0 with the boundary conditions y of 0 equal to 0 and at the end point y of L is equal to 0. Let this be equation number 1. Okay. So integrating from 0 to x. First we will integrate from this equation 1 from 0 to x. We have d square y by dx square is the second derivative. When we integrate we will get y of x. Y dash of x minus the initial point is 0. So y dash of 0 plus lambda into integral 0 to x y of first of all we have changed the variable x to some dummy variable x1. So this is y of x1 dx1 and in the right side it is 0. Now we know that we don't know what is the value of y dash at 0. So y dash at 0 is a constant. So we can write once again y dash of x as y dash at 0 minus lambda into integral 0 to x y of x1 dx1. Now again integrating this from 0 to x after converting the x variable x to another dummy variable x to convert or interchange x to x2 we will get after integration we will get y of x, the left side will be y of x minus y of 0 is equal to integral 0 to x y dash 0 dx1 minus lambda integral 0 to x integral 0 to x2 y of x1 dx1 dx2. So this is equal to y dash 0 into x minus, and we know what is y of 0. Y of 0 from the conditions given, y of 0 is 0. So the left side will be y of x is equal to y dash 0 minus x, y dash 0 into x minus lambda into, now convert the double integral into a single integral by the result we have proved, integral 0 to x minus theta y theta d theta. Now in order to find y dash of 0 we know that y of L is equal to 0. So this is our y of x, right? Now we have from the given conditions, boundary conditions, we have y of L equal to 0. So substitute x equal to L in equation number 2. We get y of L is equal to x is equal to L. L into y dash 0 minus lambda integral 0 to L. L minus theta y theta d theta. Y of L is equal to 0, that is given. So we will get y dash taking this term to the left, lambda into that term to the left and rewriting we will get y dash 0 is equal to lambda by L integral 0 to L minus theta y theta d theta. Now substitute this in equation number 2 implies y of x is equal to y dash 0 is this one, so lambda into x, so lambda x by L 0 to L minus theta y theta d theta minus lambda integral 0 to x minus theta y theta d theta. Now we can split the integral 0 to L as integral 0 to x plus integral x to L. Since 0 is the lower limit, L is the upper limit, we can take one intermediate point as x and split like this by properties of definite integrals. So we can write y of x as um, lambda x by L, lambda into integral 0 to x. When we take the integral 0 to x, we can combine the two integrals in the limit 0 to x. So this will be, when we consider 0 to x, lambda into integral 0 to x. When we take integral 0 to x, in the first one we have x by L into L minus epsilon, x by L into L minus theta minus here it is minus lambda into lambda we have taken outside, lambda into integral 0 to x minus of x minus theta, that is plus theta minus x, plus theta minus x into y theta d theta, y of theta d theta plus lambda into integral x to L x by L into L minus theta y theta L minus theta y theta d theta. Okay, simplifying this, we will get lambda into integral 0 to L. Here opening this bracket, we will get x minus theta plus theta minus x. Sorry, x minus x theta by L plus theta minus x minus x get cancelled. So this will be theta by L into L minus x. Okay. So we can write this as, after simplification, this will be theta by L into L minus x. Okay. Theta by L into L minus x, y of theta d theta, integral 0 to x plus lambda, we can take it as common, integral x to L x by L L minus theta y theta d theta, 0 to x plus x by L, like this. Or we can say that we can write this as lambda into integral 0 to L integral 0 to L k of x theta y theta d theta. So we can write this in this form, the above equation in this form, where if we write k of x theta, we can write k of x theta as theta by L into L minus x when theta is less than x, and x by L into L minus theta when theta is greater than x. When theta greater than x. So with this as a kernel, we have converted the boundary value problem into a Fredholm integral equation. So we have proved that a boundary value problem can be converted into a Fredholm integral equation. Fredholm integral equation of second kind. Okay. Uh, we can also prove that the converse is also possible. So for the converse, consider the integral equation y of x as in the split form. Y of x is lambda into integral 0 to x theta by L. Since L is constant, we can write it as theta into L minus x y theta d theta plus lambda by L integral x to L x into L minus theta y theta d theta. Okay, so differentiating we will get y dash at x is equal to lambda by L into L minus x, its derivative is minus 1. So integral minus lambda by L, we can take it as a constant. So minus integral 0 to x theta into y of theta d theta plus instead of theta we will put x. So x into L minus x into y of x minus the last term will be 0 since the lower limit is 0. Okay, plus again by Leibniz rule, when we differentiate this integral, we will get integral x to L, derivative of x is 1. So L minus theta y theta d theta y theta d theta L minus theta y theta d theta plus theta equal to L. Theta we have to substitute the upper limit. So it will be L minus L will come. So that term is 0 minus x, and instead of theta we have to put the lower limit. So x into L minus x into y of x. Now simplifying this, we see that x into L minus x y of x is there and its minus term is there. So this is equal to lambda by L into minus integral 0 to x theta y theta d theta plus x to L minus theta y theta d theta. Again differentiating, we will get y dash at x is equal to lambda by L into minus by Leibniz rule, the first integrand, the first term containing the integral will be 0 since minus, then x into y of x, second term will be x into y of x into 1 minus again 0 plus first term containing the integral is 0 by differentiating with respect to using the Leibniz rule plus giving the upper limit for theta L minus L, that will be 0 again 0, then minus replace theta by the lower limit, so it will be L minus x into y of x into 1. So this is equal to lambda by L into minus x into y of x minus L y of x minus L into y of x minus into minus plus x into y of x. So x into y of x again get cancelled. So this will be y double dash at x is equal to lambda by L into y of x. So this becomes y double dash of y double dash at x is equal to L and L get cancelled, lambda into y of x. So which is the required equation, and we have to find the conditions, boundary conditions. So from the first equation, from the given integral equation itself, we can find y of 0. Y of 0, when we give y 0 to x, we will get integral 0 to 0, that will be 0. The first integral will be 0, and in the second one there is x. So in the integrand there is x is contained in the integrand, so that will be 0. And if we substitute uh, x as L, replace x as L, this will be integral 0. First integral will be integral 0 to L, L minus L. So that integral will be 0. And the second term will be lambda by L, integral L to L. Again, that is 0. So y of L. So this is the required integral equation. Sorry, differential equation. There is one minus lambda. Sorry, this minus L into y of x is there, so this is minus y of x. That is our corresponding differential equation is y double dash plus lambda y equal to 0, y of 0 equal to 0 and y of L equal to 0. So this is the corresponding equation. Now we consider some second note. We have seen that when we convert the boundary value problem into the Fredholm integral equation, we obtained the kernel as kernel takes two values in um, when theta less than x and when theta is greater than x. That is, it is theta by L minus x when theta less than x and x by L into L minus theta when theta is greater than x. Um, so when what happens when theta is equal to x? So when theta equal to x or when x theta equal to x, both the expressions we consider both the expressions. Theta equal to x, the upper limit will become the first integral. Theta less than x, the expression will become x by L into L minus theta. Instead of x, we can choose theta also. This is same as the second one. Okay, x by L minus theta. So when theta equal to x, both the expressions are equivalent. Both expressions are equivalent. And if we consider k as a function of epsilon, now next point, if we consider k of x theta or k of theta x as a function of k as a function of epsilon and for a fixed value of theta, for a fixed value of theta, then we can see that um, then we can see that or we can write it as we will rewrite it again. Once again we will rewrite the equation for k kernel, that is k of x theta, or k of x is equal to theta by L into L minus x when x is greater than theta, x by L into L minus theta when x is less than theta. So theta is some fixed point. If theta is this point, then x greater than theta means this is values are for theta plus we are considering, and when x is less than theta means we are approaching theta through left, so that is theta minus. When we talk about the limits, so we have limit x tends to theta, mm, limit x tend to theta, k of x theta, k of x theta is this will be x by L into L minus theta. Same as in both cases, this will be the same. And what about the value of at x equal to theta, which is same as k of theta, same as k of theta. That means when we consider k as a function of x alone for a fixed value of theta, we have k is continuous at x equal to, then we can see that k is continuous at x equal to theta. Now we talk about its derivative, partial derivative. So dou k by dou x. By definition, dou k by dou x is when x is greater than theta, it is minus theta by L. When theta less than x or x greater than theta, and it is 1 minus, you can see that it is 1 minus theta by L. 1 minus theta by L when x is less than theta. That is the left hand limit, left hand derivative will be 1 minus theta by L, and the right hand derivative is minus theta by L. And at theta equal to x, we can see that this has a dou k by dou x is not continuous. At theta equal to x, or at x equal to theta, dou k by dou x is discontinuous. Since limit x tend to theta minus dou k by dou x is what? Dou k by dou x is what? Minus theta by L. Sorry, x tend to theta means when x is less than theta, that is 1 minus theta by L. And when we talk about the right hand limit x tend to theta plus dou k by dou x is minus theta by L. Both are not equal. Both are not equal. Therefore, it is not limit does not exist at x equal to theta. So, therefore, limit x tend to theta dou k by dou x does not exist. Does not exist means the limits are equal, but there are definite limits. Left hand limit and right hand limit are equal, but they are not, sorry, exist, but they are not equal. Left hand limit and right hand limit exist, but not equal. That is why the limit does not exist, and hence dou k by dou x is not continuous at x equal to theta. So this type of discontinuity is known as jump discontinuity. That means we can say that is dou k by dou x has a jump discontinuity at x equal to theta. And the magnitude of this finite jump discontinuity, um, magnitude of this jump discontinuity is actually dou k by dou x at theta plus minus dou k by dou x at theta minus the difference between the right hand limit and left hand limit. Right hand limit means we are approaching x is greater than theta. When x is greater than theta, it is minus theta by L. So minus theta by L minus when theta minus, that is when x is less than theta, that is 1 minus theta by L. So minus 1 minus theta by L. So which is equal to minus 1. So this has a jump discontinuity of minus 1. Magnitude minus 1. Okay. Thus, we have seen that dou k by dou x has a discontinuity, jump discontinuity, and it has a finite jump discontinuity of magnitude minus 1 as x increases through theta. And further, we may notice that we know what is dou k by dou x is minus theta by L and 1 minus theta by L in the two regions. And in the two regions, there is no function of theta, sorry, x. And if we consider k itself, we can see that in the two regions, k is a linear function of x. Okay, so we may notice that k is a linear function of x in the two regions, and hence dou square k by dou x square is obviously equal to 0. And one more thing, that k vanishes at both endpoints. At both endpoints, x equal to 0 and x equal to L. Now the next point, finally we may see that seen that k is symmetric. That is, k of x theta remains unchanged if we interchange the two variables x and theta. So we have k of x theta as k of x theta as theta by L into L minus x when theta less than x, and x by L minus theta when theta greater than x. Now we interchange the variables theta and x. So instead of x, we are using theta, and instead of theta we are using x. So this will be x by L into L minus theta when x is less than theta, and this will be theta by L into L minus x when x is greater than theta. That is the same, that is when x greater than theta means theta less than x. So theta, when theta is less than x, we have theta by L into L minus x, both are same. And when theta is greater than x, we obtain k theta x as x by L into L minus theta. And here also when theta is greater than x, we have obtained it as x by L into L minus theta. So this is, these are the same. K of theta x is same as k of x theta. That means the kernel is symmetric. So in this problem, the kernel is symmetric. There are interesting properties for symmetric kernels that we will discuss in later. So let's stop here. Thank you. Thank you all.